Hello, this is Mr. P, and today we're going to talk about mathematical induction. And to do that, we're going to use the example of this series. And the proper way to read this notation would be the sum. This is the Greek letter sigma. It's the uppercase version of the Greek letter sigma, which really means sum. And I is going to be our indexing variable, and we're going from 1, which is our lower bound, to n, which is the upper bound, and our expression is I. So the way to read this would be the sum as I goes from 1 to n of this expression. So when we expand it, we simply replace I with 1 for our first iteration, and then we add when we replace I equals 2 in our second iteration, and add when I equals 3, etc. So we end up getting this series. When I is 1, we get the first term. When I is 2, we get the second term, and then we sum all those terms. So this is basically the sum of the natural numbers or the counting numbers from 1 to n. And when we talked earlier about the arithmetic sequences, we talked about the story of a young Carl Friedrich Gauss who came up with a way to find a shortcut for this calculation. And that led to the following formula, which is n times n plus 1 all over 2. And we demonstrated that this worked for the case when n equals 100. The teacher made him add all the numbers from 1 to 100. And it was a good demonstration, but it is by no means a proof. We demonstrated it works for the case when n equals 100, but we need to prove it works for all cases. And for that, we want to use mathematical induction. It's a method of proof that is well suited to proving multiple cases, or in this fact, an infinite number of cases. And mathematical induction is a two-step process. Our first step is to show that this formula is valid for the base case. So step 1 is we show it's valid for n equals 1. And that's a simple matter of replacing n with 1 on the left side. So if we look at our expression here, we're going to say that the sum as I goes from 1 to 1 of I means we only plug in the first term. 1 is our upper bound and our lower bound, so we're only looking for one term, which is 1. And then the right side, when we replace n with 1, we get this expression. And of course, 1 plus 1 is 2, so we get 2 over 2, which does equal 1. So the left side equals the right side, so we can say that step is complete. We have shown it's valid for n equal to 1. Now, our second step is to make an assumption. It's what we call the assumption hypothesis. And the correct way to do that is to take the statement that we're trying to prove for all values of n, for all integer values of n, and we want to make a change of variables. And it's very important to make this change of variables. So really, this is going to be our assumption hypothesis. Instead of n, which represents all values, we're going to replace it with k, which represents a single case. So we're going to assume that this formula is valid for one single case that we're going to call k. And it's a perfectly valid assumption because we saw in the step before that it is true for when n equals 1. So now we're looking at our assumption hypothesis, which we're going to show that if it's true for the case k, then it will also be true for the case k plus 1. So on our strategy basically is to replace k with k plus 1 on both sides and show that it will still be equal. On the right side, that's very simple to do on the right side. Again, we're going to replace k with k plus 1, and we're going to show that replacing k with k plus 1 here gives us k plus 1, and replacing it in this parenthesis gives us k plus 1 plus 1, which gives us k plus 2. So replacing k with k plus 1 yields our goal, which is k plus 1 times k plus 2 all over 2. We want to keep this idea in mind for the left side when we're doing the algebra. So on the left side, when we replace k with k plus 1, we do so like this. The upper bound now becomes k plus 1. We're still starting at 1, but instead of stopping at k, we're going to go one more term. So when we do the expansion, we're going to we're going to do everything we did before, and then plus one more term, the k plus 1 term. And now the rest is the key step, basically, is that we do the assumption hypothesis in order to be able to make a substitution. Just about every time you're going to do an induction proof, you're going to make this key substitution, which will be from 1 to k. We already have an expression for that. It's k times k plus 1 over 2. So we're going to make that substitution. From 1 to k is this expression. And remember, we're assuming this to be true, so we can make that substitution. And then it's plus one more term, of course. And the rest is just the algebra. We want to show that this expression is equal to this expression. And keeping your goal in mind will help you get through the algebra. First of all, you notice this is all one term. It's a numerator over denominator. So here we want to combine these two terms. So in order to do that, you have to have a common denominator. So the first fraction we're going to keep the same, no changes to the first fraction. But since 2 is the denominator, we want to rewrite the second one so it's something over 2. So we go ahead and make a common denominator. And now we can combine the two terms to get this expression. And now the next step sometimes confuses students, but remember, you want to keep your goal in mind. Notice how this is in factored form. This numerator is in factored form. So on this side, we want to factor it if we can. Here we can directly factor it because this parenthesis and this parenthesis are the same. So we can factor out that common parenthesis. If they were not the same, we would have to distribute and then combine like terms so that we got a trinomial, and then we would factor that trinomial. But luckily, we can just factor out the common k plus 1, and that leaves the k and the plus 2 behind, so that becomes the other parenthesis. And you'll notice that is exactly what we're looking for, so therefore, we've met our goal for the second step. Now, putting these two logical steps together, remember, we're saying that this statement is true for our base case, which is n equals 1. And then the second part says, if it's true for any case, that let's call it k, then it will also be true for the next case, which is k plus 1. So therefore, if it's true for n equals 1, then it's also true for n equals 2. If it's true for n equals 2, it's also true for n equals 3, and so on and so forth. So therefore, we're saying that it's true for all positive integers. And now we're ready to put it all together. We can say that, therefore, the formula is valid for all n such that n is an element of, or a member of, the positive integers. And we're done.